Welcome dear students. Myself again, Dr. Ajay Semilti from HNB Garhwal University. Welcome you in the series of lecture on no water-based systems. So far we have discussed, recently we discussed the cyclodextrin complexes, and in the cyclodextrin complexes we have discussed what is cyclodextrin, what is the importance, what are the types of cyclodextrins, parent cyclodextrin, derivative cyclodextrins, selection of drugs for the cyclodextrin complexation, methods of preparation of cyclodextrin complexation, and methods of improving the efficiency of cyclodextrin complexation. In this lecture, we are going to discuss the characterization of cyclodextrin complexes and their application or advantages in detail. So let us start our discussion. After completing this lecture, dear students, you will be able to characterize the cyclodextrin complexes, to correlate the characterization results, and use the cyclodextrin complexes for various advantages. Okay. We will be covering this lecture under the heads characterization of cyclodextrin complexes, the methods, correlation of the different methods, advantages, and application of cyclodextrin complex. Cyclodextrin complexes, as we are just moving, just to recall that they are the amphiphilic molecules, a hydrophilic outer surface and a lipophilic center cavity that can accommodate a wide variety of lipophilic drugs we can prepare. And just we are recalling that the complexion of drugs inside the hydrophobic cavity of cyclodextrin is there. Hydrophilic exterior it is having and hydrophobic cavity it is having. So the drug which will go inside with or without any hydrophilic excipient, like in case of, as you are seeing here, in the case of acyclovir, we have used nicotinamide and PVP as a hydrophilic excipient. With the kneading method, we prepare the acyclovir cyclodextrin complexes. Now let us discuss how we can characterize. The characterization of CD complexes can be done by the spectral analysis like FTIR, NMR, surface morphology, SEM, or size may be taken up by the SEM as well as the DLS, dynamic light scattering or laser scattering we say, crystallinity through the solid state characterization like XRPD. We will be also discussing some of the aspects, some of the new aspects, thermal analysis, DSC, differential scanning calorimetry, solubility, permeability, in vitro drug release, permission study, and in vivo studies are the major characterization parameters. These are not just limited. This characterization is not limited to this thing. Depending upon the complex you are preparing, depending upon your desired characteristic, the characterization parameters may be more, but these are the most common and general characterization parameters for cyclodextrin complexes. Now first is spectral analysis by FTIR or NMR. FTIR, the infrared spectroscopy, shows some changes but not clear evidence is observed. There. Bands due to the included part of the guest molecule do shift or their intensities are altered. But since the mass of the guest molecule does not exceed the guest molecule does not exceed from 5 to 15% of the mass of the complex, these alterations are usually obscured by the spectrum of the host. This is the most common thing. That's why with the FTIR, the solid conclusion, solid inferences to interpret FTIR is very typical in case of cyclodextrin complexes. NMR shows some shifts in some cases clearly. However, the interpretation again demands expertise in NMR analysis and interpretation. Surface morphology, we perform the SEM. With the SEM, we may see the surface morphology, which may be correlated with release and other parameters. We can also have the idea about the particle size of the complex. We can also perform the particle size analysis with DLS we can have an idea with the laser scattering. We can have an idea of the the particle size of the cyclodextrin complexes. However, it depends that whether the particle size in the range of the DLS, okay, which DLS can determine. Crystallinity is one of the most important parameter because it is the crystallinity which is being converted from uh, crystalline to the amorphous one. So the XRPD can indicate the complex gives a different X-ray pattern, diffraction pattern compared to the physical mixture of the host and guest molecules. So by this we can have an idea. We will be discussing with examples. We are not just limiting to this discussion only. Thermal analysis, DSC can be done. Why we do the DSC? Actually to confirm whether the complex has been actually formed or not, whether the thermal changes are there or not. The complex formed may have a different melting point, different thermal properties, or they have they may show the no melting endotherm uh, because of its amorphous nature. The physical mixture of in most cases will still exhibit the melting endotherms of the substance of the drug and the cyclodextrin if it is crystalline. Okay, so by this way we can have some idea about the complex, and we'll be discussing with examples. Moving to solubility, permeability, we do by the standard methods like in vitro drug release, also standard methods, permission in vivo studies, depending upon your requirement, the suitable pharmacological models can be taken and the in vivo studies can be performed. Now I'm taking example of amphotericin B. Amphotericin B, can you guess in which class of BCS it is? Yeah, any guess? Any wild guess? BCS class 1? No. Not 2. It is class 4 drugs. It has got the low solubility and low permeability. So we have taken up this amphotericin B. It is basically antifungal drug. As you can see, it is a huge drug with respect to the molecular weight and also with respect to this structure. So as you can see, we have taken this from a study in which the computer modeling was given there. So what happened that amphotericin B can interact in any way. Either it may go from the open part of the bucket of the cyclodextrin or from the low narrower part, or it may involve more than two. Basically, it is hypothesized because it is a huge structure, so it requires more than two cyclodextrin buckets to be complexed. For the complexation, it is always 1:2, 1:3, or maybe the higher ratios of the drug is to CD is desired when we are going for the complexation of this kind of drug. The orientation of the may get changed because this orientation may be from the wider part or from the narrower part. So drug may entrap there into the cavity from any of the portion, any of the open portion. Let's see with a unique example with acyclovir BCD complex we studied. That as you can see in this diagram, that drug at the bottom, it is the DSC curve of the bottom. DSC curve of the drug is there at the bottom, and acyclovir is drug. Then upper one is the beta cyclodextrin. Then above it is PPK30 nicotinamide. Then its physical mixture you can see, and above all are the formulations of cyclodextrin complexes. You can see that DSC is clear cut. There is a there is no endothermic peak there in case of cyclodextrin complexation. So it's clear cut that the drug peak has shifted and the endotherm has gone there. So that endothermic peak is not there in that parent position. So the change is clearly visible in the DSC. Another example from the same drug is cyclovir BCD complex. Now we are seeing the X-ray diffraction. Now what's the difference? At the bottom of this diagram, you can see the sharp crystalline peak of the drug is cyclovir. Okay, and then BCD's peaks are there in X-ray diffraction. Then PVP, nicotinamide, physical mixture, and above all are the formulations. So formulations are having the diffuse peak rather than the crystalline one as compared to the drug, and the drug's sharp endothermic sharp crystalline peak is not there in case of complexes. So a partial amorphization is indicated here in case with the X-ray diffraction of a cyclovir. So we can interact that and we can compare it with the DSC. So we can correlate this data not only with the DSC but also with the scanning electron microscope, the surface morphology. We can compare that how the changes are correlated with the DSC. If there is a change in endothermic peak and there is a complete disappearance of endothermic peak in case of DSC, certainly the change will be there in XRBD. And this will be in good tune. Now again taking another example, glimepiride XRPD study, it is one of our work. So again we can see that the changes are here in the, and we can see also the difference between the two methods. Here we have seen the difference between the two methods, solvent evaporation kneading method, the complexes were prepared and the change in the X-ray diffraction was clear cut observed here. Okay. Now what's this? This is our pride of India. Atoms in the service of the nation. Can you guess? Yes, it is our Cyrus and Dhruva reactor, Bhabha Atomic Research Center, BARC. Why I am showing it? Let's see. I have been fortunate enough to work with the India's top scientist on the metal physics, on the solid state physics. In collaboration with the in the projects of the UGC DAE CSR, UGC Department of Atomic Energy Consortium for Scientific Research, Mumbai Center, I have been working on the drug cyclodextrin complex interaction. Professor Aswal, VK Aswal is our collaborator, is our principal scientist there. So what we are doing, it is complete metal physics. How we can imply these techniques? Let's see. Actually, what you are seeing here is a setup prepared by the scientists themselves. There's their in-house preparation there. What is happening that the whatever the neutrons flux coming out of the reactor, the nuclear reactor, research reactor Dhruva, it is being taken and directed that line, and it is directed to the sample, and the neutron scattering is observed as X-ray diffraction gives the that pattern. In the similar manner, you can say neutron scattering is observed. So it is a setup for small angle neutron scattering. So we have been using this small angle neutron scattering, and in India this is the only lab which provides the SNS, and in the world there are a couple of, if not more than 20 maybe this kind of setup are available. So this is the setup what they have done, that in the after the biological field of the reactor, with the monochromators have been placed there, and the neutrons have been directed to a sample slate, to a sample, and through a slate it is received at a detector, and detector sense the scattering, and this scattering is is in proportionate to the size and shape of the because rather this the shape we can interpret very effectively and very precisely for the nanoparticles and for these kind of complexes. Okay. However, I'm not going to detail it as a very big topic. That So what we can do with the in the two vectors when the this we can have an idea depending upon the SAS fitting, that small angle scattering fitting when we perform. This provides a real space interpretation. As you can see, if you see the blue one, okay, it is indicated that the size of this aggregate, that composite, is like that. If you see the red curve there, it means it is spherical one, and by this, if it is green, it is like, disc shaped there. So depending upon the size, the scattering is there. So on the basis of scattering, we can interpret the shape, and even the size of that composite can be precisely determined. Okay, why we did this thing, that when we performed the amphotericin B, we went for the amphotericin, because the problem with the small angle neutron scattering is only the high molecular weight drugs can be gives the better scattering. Otherwise, for the smaller molecule, you have to go for the low Q values. So SNS data of all the analyzed samples are plotted between the log of wave vector Q at x-axis versus the log of intensity factor at the y-axis. So what we have done here, that we have prepared the randomly methylated beta cyclodextrin complex of amphotericin B, and we saw that you can see the red one is the randomly methylated beta CD scattering is there, and the other two are the its complex of different proportion. I'm not opening up the proportions here. uh, what we saw, what we concluded, that actually when we are preparing the cyclodextrin complexes, there is a utmost problem that not FTI doesn't give much information. NMR, it is very typical to get the interpretation, and many times the things are meshy. So to be very precise, what is happening inside what is happening in between them, drug and cyclodextrin, we want to go for that SNS, and we were lucky enough that we got that opportunity to work with the top scientists of India, and and we had a good interaction and with those people who were expert in these things, and we tried to interpret the things, we tried to study these interactions. We saw that, we found that the BCD is basically the porous cylinder shape of 7.2 angstrom radius and length of 7.8 angstrom with some aggregates there here when we prepared the complexes. Then these are analyzed only in D2O. Okay. In the case of drug BCD complex, it was found that these cylinders with the radius of 7.2 angstrom and length of 7.8 angstrom, they form some spherical host guest interaction house with a radius of 126.2 angstrom with the presence of some free CDs. You cannot say that free CDs are not available, are there. You can't say. You can't deny the existence of free CDs in the complex even. So, and it was confirmed there in this study of small angle neutron scattering, that free CDs are always there with this thing, and the composite was spherical one. So by this data, we could see that the hydrophobic interaction with different CDs, and that too at different planes, might have resulted into the final amphotericin B and beta cyclodextrin or that HPBCD or RMBCD complex model. So we studied with all other derivatives, not only with the RMBCD, and tried to interpret that what is actually happening there. Though SAS fitting was well supported by some previous studies also. So it was a wonderful experience to walk with the people, and you can also have, if you have a genuine problem, good rational, and your problem definition is very crystal clear, you can also get the beam time there. You can apply the beam time, and with the proposal, you can talk to the people there, and the various other analytical facilities like neutron powder diffraction and other related studies can also be done there. Okay. So Again here, we can see that with this SAS fitting graph, whatever kind of curve it is we are getting in the after the SAS fitting of data, we get the data, we get ample of data. We do the SAS fitting there. SAS fitting is freely available open source software programming there, and you can get the data feed. You can get the data from the analysis, and then you will fit the as per your hypothesis, and you will see that whether your hypothesis is good or not. So we did the same and tried to explain that how amphotericin B would have interacted with the cyclodextrin. Okay. So what are the advantages? The complexation, the cyclodextrin complexation is a very useful technique for improving the solubility and stability of class 2 glibenclamide, glimepiride, limestide drugs and class 4 drugs like furosemide, amphotericin B. Cyclodextrin might also alter the lipid barrier of the absorption site, which may contribute to the enhanced drug absorption. And oral viability of poorly water soluble drugs can be improved by enhancement of the dissolution rate and or apparent solubility. Physical stability of compounds in their metastable forms such as amorphous can be enhanced by the inhibition or prevention of crystal growth. Content uniformity of a small amount of a drug in bulky diluents can be ensured by an increase of dispersibility and fluidity. Shelf life of drugs can be extended by increasing their stability. If we'll increase the stability, especially if we say we have done the work on with doxycycline, the photostability, doxycycline has got the very good solubility. You may ask that's why you are preparing the cyclodextrin complex or doxycycline. It has got wonderful water solubility. But the problem is, our rationale is that it is not photostable, and cyclodextrin may increase the photostability of the doxycycline molecule. Okay, and we have proved it with some for studies. Liquid preparations like solubility and stability and or stability of the drug in water can be improved with the help of cyclodextrin complexes. In case of suspensions and emulsions, caking, creaming and phase transition can be suppressed by the protective sheet of the cyclodextrins. Thixotropic nature. The thixotropic nature of suspension can be controlled with the help of cyclodextrin complexes, and physical stability of the dispersed system can be improved with the help of cyclodextrin complexation. In case of semi-solid preparations, topical bioavailability can be improved by enhanced release of a drug from ointment or suppository basis. Water absorption capacity of oleaginous and water-in-oil bases can be improved by hydrophilic cyclodextrins. In the case of injectables, solubility and stability of the drug in water can be improved. Drug-induced hemolysis and muscular tissue damage can be reduced. Solubilized products can be prepared by freeze-drying cyclodextrin complexes if needed for enhanced stability. Suspensions for parenteral use can be prepared by reducing the drug to a fine powder containing the cyclodextrin complex by use of ball milling. But some limitations are also with the cyclodextrin complexes. We have covered these advantages. Okay, the characterization parameter we have seen. The API. Now it's the turn of limitation. The API has to be able to it should be able to form the complexes with a selected ligand. First of all, the compatibility. It should be able to to form a complex. First thing. Method failure may be there for the complexes of AP type, dilution of a system. If you dilute that particular system, it may result in precipitation. Then potential toxicity issues, regulatory and quality control issues related to the presence of the ligand may add to complications and also to the cost of the development process. The complexation efficiency is often rather low in case of cyclodextrin complexation, but it is relatively what is the reason that relatively large amount of CDs are typically required to achieve desirable solubilizing effect. We need more, as compared to drug, we need more and more amount of large quantity of cyclodextrins are required to form the to have the effective solubilizing effect. But still, It's a very promising molecule. And the most important thing is its safety is well known. It is very widely used, and thirdly, what I would say, it is very cost effective. So if we can use this for novel drug delivery, for targeted drug delivery, it would it would bring about wonders in novel drug delivery. I promise you. So that's why the people are working on this molecule and this complex cyclodextrin complexes for novel drug delivery and targeted drug delivery. These are some of the references. We have been working for a quite long time on the cyclodextrin complexes as well as the lipid complexes. You can go through these references. Now let me summarize. Cyclodextrins are cyclic oligosaccharides. They are the enzymatic degradation product of bacterial enzymatic degradation products. They form amphiphilic complexes. There are different methods of characterization. We have studied the different methods of preparation in the last lecture. Okay. Now the methods of preparation. After the methods of preparation, characterization methods include the checking the crystallinity, its solubility, complex formation, release, in vitro release, you can say permeability, bioavailability, and for these you adopt various spectral techniques, SEM, you go for DLS, you go for XRPD, X-ray powder diffraction, differential scanning calorimetry, and we have introduced you with SANS, small angle neutron scattering. Neutrons scattering can be very useful, but please remember this is a mega facility, only one in India, in BRC, Bhabha Atomic Research Center, Mumbai. If we have a genuine or some other issues in which you want to go for the characterization for with the help of neutron scattering, you can go and apply for the beam time from the BRC or the UGC DACSR Mumbai Center. So good correlation is needed in between the characterization parameters. Okay, you should correlate your data, your results, your inferences must be correlated with each other. The solubility, XRPD, DSC, in vitro release. These data, these results must correlate, must be in good tune with each other. The solubility, permeability, stability is improved, and the geometric complexation, it is remember, it is a geometric complexation, okay, where the functional complexation is there in the lipid complexes. Okay, the geometry doesn't play the role in the lipid complexation, but here it plays the role. So but the basic problem is low complexation efficiency is there. You require more of the cyclodextrins. So this was all about the cyclodextrin complexes, and these complexes can be used for a variety of purposes as we have discussed. Please, with exam point of view, you must know what is cyclodextrin, what are the types of cyclodextrins, solubility, their parent cyclodextrins, methods of preparation and characterization, and their application part. Not only solubility, they increase the stability, permeability. You must know in entire scenario, you must know what is the role of cyclodextrin complexes, and the characterization parameter you must know, and with the capability of correlating one parameter with other parameter. Okay, so this was all about the cyclodextrin complexes. Hope you have got some new information from this lecture, and I welcome you to avail the government facilities of the UGC DACSR, and for free they are available. So this is all for this topic, and we'll be coming with a new lecture in our series. In the next lecture, we'll be coming back again with you with a new lecture. Thank you for being with us, and practice, learn these things for your exams. Okay, thank you and happy learning.